Langchain Fireworks Chat Models. Langchain Fireworks Chat Models Framework, a comprehensive framework for building custom chat models. Using the powerful combination of langchain and fireworks, this framework empowers developers to create tailored conversational experiences by leveraging the capabilities of these libraries. Inputs. User input: the input provided by the user, typically in the form of text, initiating the conversation with the chat model. For example, what is the capital of France? Context: additional information relevant to the user's input, providing the chat model with context to understand and respond more accurately. This might involve past conversations, knowledge base information, or external data sources. Imagine a user asking what is the latest news about Tesla, providing context like I am interested in their electric vehicle production. Outputs. Chat response: the output generated by the chat model in response to the user's input and context. This can be a textual response, a summary of information, or even a structured output like a list or table. For instance, the response to what is the capital of France could be the capital of France is Paris. Steps. Define a prompt: the process of crafting a clear and specific instruction for the chat model, guiding it to generate the desired output. This involves specifying the task, providing relevant information, and structuring the input format. For example, a prompt for summarizing the news article could be: summarize this news article in 100 words. Insert article text here. Use langchain to chain together components: the core functionality of langchain, allowing you to assemble a sequence of components, such as language models, data sources, and tools, to create a complex and sophisticated chat model. This modular approach enables you to tailor the model's behavior to specific use cases. Picture a chatbot that accesses a knowledge base to answer factual questions, uses an API to retrieve current weather data, and then synthesizes the information into a coherent response. Build a custom chat model, the culmination of the framework, where you combine the defined prompts, chained components, and desired output format to create a functioning chat model. This model can be a standalone application, integrated into an existing system, or deployed as a service. Consider a chatbot for a customer support system that understands customer queries, retrieves relevant information from a database, and provides helpful answers. Deploy and use the model, making the custom chat model accessible to users, enabling them to interact with it. This involves deploying the model in a suitable environment, handling user interactions, and providing feedback mechanisms. Imagine a chatbot deployed on a company website, answering user queries about their products and services, offering personalized recommendations, or providing customer support. Prerequisites. Langchain, an open source library that provides tools for building and connecting different components to create powerful language models. Langchain allows you to chain together various language models, data sources, and tools to create custom, context-aware applications. A real-world example could be using langchain to integrate a question-answering language model with a knowledge base, enabling your chat model to access and retrieve information from a specific domain. 0.0.124 The specific version of langchain required for this framework. This ensures compatibility and guarantees that the framework functions as intended. Fireworks, a library that facilitates building and deploying custom chat models, simplifying the process of creating and managing conversational experiences. Fireworks provides tools for prompt engineering, model selection, and deployment, streamlining the creation of chat models. A practical example could be utilizing Fireworks to easily deploy your custom chat model as a web service, making it accessible to users through a web interface. 0.3.4 The specific version of Fireworks required for this framework. Ensuring compatibility and smooth operation. Fine-tune parameters. Prompt engineering: the art and science of designing effective prompts that elicit desired responses from language models. This involves crafting clear instructions, providing relevant context, and structuring the input format to guide the model towards the desired output. Imagine a prompt for summarizing a news article. Please summarize this news article in a concise and objective manner, highlighting the key events and their significance. Model selection: the process of choosing the appropriate language model for your chat application, based on factors like model size, training data, and performance characteristics. Different models excel in different tasks, so selecting the right one is crucial for achieving desired results. For example, a large language model might be suitable for general-purpose conversation, while a specialized model trained on legal documents could be more effective for answering legal questions. Chain configuration: the process of defining and configuring the sequence of components in a langchain chain, specifying the order of execution, input and output formats, and how components interact with each other. This allows you to tailor the chain's behavior to your specific needs. Imagine a chain that first retrieves relevant information from a knowledge base, then uses a language model to summarize the information, and finally uses a text-to-speech engine to generate an audio response. Challenges and fixes. Model performance issues: situations where the chat model does not perform as expected, including issues like slow response times, inaccurate outputs, or inconsistent behavior. Check model configuration: examining the model's settings and parameters to identify potential errors or misconfigurations. This involves reviewing the prompt, the chain configuration, and the model's training data. Consider a case where the model is not generating coherent responses. Checking the model configuration might reveal that the prompt is poorly formatted or that the model is not trained on data relevant to the task. Fine-tune the model: adjusting the model's parameters or training it on additional data to improve its performance. This involves customizing the model's behavior to better suit the specific needs of your application. For instance, if the model consistently generates biased responses, fine-tuning it on a dataset that promotes fairness and inclusivity might help address the issue. Slow response times: situations where the chat model takes a long time to generate responses, impacting user experience. Optimize code: improving the efficiency of the code implementing the chat model, reducing unnecessary computations and optimizing resource usage. This might involve using more efficient algorithms, data structures, or libraries. Consider a case where the model's response time is slow due to complex calculations. Optimizing the code might involve streamlining the calculations, using more efficient data structures, or leveraging hardware acceleration. Use efficient tools: leveraging efficient tools and libraries that optimize performance, such as using faster language models, employing optimized data structures, or utilizing specialized hardware. For example, utilizing a smaller, faster language model might significantly improve response time without sacrificing accuracy. Inaccurate responses: situations where the chat model generates incorrect or misleading responses, impacting the reliability and trustworthiness of the model. Improve prompt engineering: reevaluating and refining the prompts used for the chat model, ensuring they are clear, specific, and guide the model towards accurate responses. This might involve providing more context, clarifying the desired output format, or using examples to illustrate the desired behavior. Consider a situation where the model generates incorrect answers to factual questions. Reviewing the prompt and providing more specific instructions might improve the model's accuracy. Increase context size, expanding the context provided to the chat model, enabling it to access more relevant information and generate more accurate responses. This might involve providing additional background information, historical data, or relevant documents. For instance, a model struggling to answer questions about a specific topic might benefit from accessing a larger corpus of texts related to that topic. Fine-tune the model, adjusting the model's parameters or training it on additional data relevant to the specific task, improving its ability to generate accurate responses. This involves tailoring the model's knowledge and understanding to better suit the desired outputs. For example, fine-tuning the model on a dataset of verified factual information could significantly improve its accuracy in answering factual questions. Limited context, situations where the chat model lacks sufficient context to provide comprehensive and meaningful responses, resulting in incomplete or irrelevant outputs. Use a vector database, integrating a vector database to store and retrieve relevant information for the chat model, enabling it to access a wider range of context. This involves indexing relevant documents or knowledge base entries and using similarity search to retrieve relevant information based on the user's query. Consider a scenario where the model needs to access a large corpus of text documents. Using a vector database allows the model to efficiently retrieve relevant documents based on a user's query, providing richer context for the model's responses. Employ retrieval augmentation, a technique where the chat model retrieves relevant information from external sources, such as websites, articles, or databases, and uses it to augment its responses. This involves querying external sources, extracting relevant information, and integrating it with the model's outputs. For example, a chatbot answering questions about current events might leverage retrieval augmentation to access and incorporate relevant news articles into its responses. Limited domain knowledge, situations where the chat model lacks sufficient knowledge about a specific domain, limiting its ability to provide accurate and relevant responses. Train on domain-specific data, training the chat model on a dataset specific to the domain of interest, enhancing its understanding and ability to generate accurate responses. This involves providing the model with domain-specific documents, articles, or data sources to learn the nuances and vocabulary of the domain. Consider a chatbot designed for a financial services company. Training the model on financial news articles, reports, and regulatory documents would improve its knowledge and ability to answer financial-related questions. Fine-tune with relevant knowledge, adjusting the model's parameters or training it on relevant knowledge sources, improving its ability to provide accurate and insightful responses within the domain. This involves incorporating domain-specific information and insights into the model's training process, enabling it to understand and generate responses aligned with the domain's context. For example, fine-tuning the model on a dataset of customer reviews for a specific product could help it provide more accurate and relevant responses to customer inquiries about that product. Ethical concerns, potential issues related to bias, fairness, safety, and responsible use of the chat model, requiring careful consideration and mitigation strategies. Ensure model fairness, designing and training the model to be fair and unbiased. minimizing the potential for discriminatory or harmful outputs. This involves analyzing the training data for bias, implementing techniques to mitigate bias, and continuously monitoring the model's outputs for potential fairness issues. Imagine a chatbot designed to provide recommendations. Ensuring fairness involves making sure the recommendations are not biased against any particular group or individual. Implement safety measures. Incorporating safety measures to prevent the model from generating harmful or offensive outputs, including measures to detect and mitigate potential risks. This involves developing mechanisms to identify and remove inappropriate content, filtering harmful language, and implementing controls to prevent malicious or unsafe interactions. For example, a chatbot might use a safety filter to prevent it from generating responses that are offensive or contain inappropriate language. Address bias. Actively identifying and addressing potential biases in the model's outputs, ensuring that the model generates fair and equitable responses. This involves continuous monitoring of the model's performance, analyzing outputs for potential bias, and implementing corrective measures to mitigate bias and promote inclusivity. For instance, a chatbot designed to provide customer support might be trained on a dataset that includes diverse customer voices, helping to mitigate bias in its responses and ensuring fair treatment of all customers. Langchain Fireworks Chat Models Summary: a framework that enables the development and deployment of robust conversational AI applications. Utilizing a powerful combination of large language models (LLMs) and tools. Delivering engaging and insightful interactions. Inputs. User input refers to the text provided by the user to initiate or continue a conversation with the AI application. This input can be in the form of questions, requests, or statements. Contextual information represents the background knowledge relevant to the current conversation. It includes past interactions, relevant data, and other information that helps the AI understand the user's intent and provide accurate and contextually relevant responses. Outputs. Generated responses are the text outputs produced by the AI application in response to user inputs. They can be in the form of answers, suggestions, summaries, or any other type of information relevant to the conversation. Actionable insights are valuable pieces of information derived from the conversation that can be used to make informed decisions or take specific actions. They can be in the form of recommendations, predictions, or analyses based on the context of the conversation and the information provided by the AI. Steps. Defining the desired conversational flow involves designing the structure and logic of a conversation. This includes determining the types of questions the AI should ask, the information it should provide, and the overall flow of the interaction. Selecting appropriate LLMs and tools is a crucial step in building a powerful conversational AI application. LLMs, such as GPT 3.5 or GPT 4, provide the ability to understand and generate human-like text, while tools like APIs or databases can enhance the application's capabilities by providing access to external data and functionalities. Configuring the workflow involves setting up the interactions between the LLM, tools, and other components of the application. This involves defining the specific tasks each component performs, the data flow between them, and the overall logic of the conversation. Deploying and monitoring the application involves making the application available to users and tracking its performance. This includes setting up the infrastructure for hosting the application, managing user access, and collecting data on user interactions to improve its functionality over time. Prerequisites. Python programming language is a widely used high-level programming language known for its readability and ease of use. It is often used for developing AI applications, including conversational AI. Langchain library is a powerful open-source library that provides a framework for building and deploying AI applications that interact with LLMs and other tools. It simplifies the process of integrating LLMs into applications, allowing developers to focus on building the conversational flow and logic. LLM models are powerful AI models trained on vast amounts of text data, enabling them to understand and generate human-like text. Popular examples include GPT 3.5 and GPT 4, developed by OpenAI, which are known for their ability to generate coherent and engaging text in response to a wide range of prompts. Fine-tune parameters. Prompt engineering is the art of crafting effective prompts that guide the LLM to generate desired outputs. It involves understanding the LLM's capabilities and limitations and designing prompts that elicit the most accurate and relevant responses. Model selection involves choosing the right LLM for the specific application. This requires considering factors such as the LLM's capabilities, its cost, and its availability. For example, if the application requires generating creative content, a more powerful LLM like GPT-4 may be preferred. However, if the application focuses on simple tasks, a smaller and less expensive model might be sufficient. Challenges and fixes. Integration complexities arise from the need to connect and coordinate multiple components, such as LLMs, tools, and databases, within the application. Maintaining conversational consistency involves ensuring that these responses are coherent and relevant to the ongoing conversation. This requires managing the context of the conversation, remembering previous interactions, and providing responses that align with the user's intent. Handling user errors involves gracefully managing unexpected or invalid user inputs. This includes providing clear error messages, guiding users towards correct inputs, and potentially redirecting them to relevant resources for help. Scalability and performance refer to the ability of the application to handle increasing user traffic and workloads. This requires optimizing the application's architecture, leveraging cloud resources, and implementing efficient data management strategies. Langchain Exa Retrievers Exasearch Retriever. None. Finding documents most similar to a given query, even if the query contains words not present in the documents. This strategy leverages the power of vector representations to capture semantic similarity and retrieve relevant documents from a large corpus stored in an Elasticsearch index. Inputs. The text of the query for which you want to retrieve relevant documents. For example, what are the key benefits of using LangChain? The name of the Elasticsearch index that contains the documents you want to search. This index should be configured to store text embeddings for each document. Outputs. A list of documents ranked by their similarity to the query. This list contains documents most relevant to the query, even if they do not contain all the words present in the query. Steps. The query text is embedded into a vector representation using a LangChain embedding model. This vector captures the semantic meaning of the query. The embedded query vector is used to perform a sparse search within the Elasticsearch index. Sparse search techniques are optimized for finding similar documents even when the query contains words not present in the index. The Elasticsearch search results are retrieved and sorted based on their similarity to the query. Documents with higher similarity scores are ranked higher in the results list. Prerequisites. The Elasticsearch index must be configured to store text embeddings for each document. This usually involves adding a field to the index schema for storing the embedded vector representation of the document's text. For example, a field named text embeddings would store the vector representation of the document's text. Langchain needs to be configured with an embedding model that supports sparse search. Popular choices include sentence transformers and OpenEye embedding models. These models are capable of generating vector representations that allow for efficient sparse search. Fine-tune parameters. This parameter specifies the number of documents to retrieve from the Elasticsearch index. Increasing this value will return more results, but it might also include less relevant documents. Similarity metric. This parameter defines the similarity function used to compare the query vector with the document vectors in the Elasticsearch index. Commonly used metrics include cosine similarity and Euclidean distance. Challenges and fixes. Queries may contain words that are not present in the indexed documents. This can lead to poor retrieval results if the search relies solely on exact keyword matching. Fixes to challenge 1. Sparse search techniques are used to overcome this challenge. These techniques efficiently find documents that are semantically similar to the query. Even if they do not contain all the query terms, this is achieved by considering the vector representation of the query and comparing it to the vector representations of the documents in the index. Finding the optimal settings for the K parameter and the similarity metric can be challenging and require experimentation to achieve the desired level of accuracy. Fixes to challenge 2. Experimenting with different values for K and similarity metric is recommended to fine-tune the retrieval process for optimal results. It is also helpful to consider the specific embedding model used and its characteristics. For example, some models might perform better with different similarity metrics. Additionally, experimenting with different embedding models altogether can lead to improved accuracy. Langchain XR tools XR find similar results. Summary of Langchain XR tools XR find similar results. This tool helps find similar results based on a given query and a document. Inputs. A query, a question that the user asks, for which similar results are needed. A document, a piece of text that contains information related to the query. Outputs. Similar results from the document that are relevant to the query. Steps. 1. Load the document into the tool. 2. Extract the embeddings from the document using an embedding model. Embeddings are numerical representations of text that capture its meaning. 3. Find similar results by comparing the embeddings of the document with the embeddings of the query. Prerequisites. Embeddings model. A model that converts text into embeddings. For example, OpenAI embeddings. Sentence transformers. Vector database. A database that stores and searches embeddings efficiently. For example, Chroma. VV8. Pinecone. Fine-tune parameters. Similarity threshold controls how similar the results need to be to the query. A higher threshold means only very similar results will be returned. Number of results to return controls the maximum number of similar results returned. Challenges and fixes. Challenge 1. No similar results found. Fixes to challenge 1. Increase the similarity threshold. Relax the similarity requirement to include more results. Increase the number of results to return. Return more results even if they are not as similar. Challenge 2. Too many similar results found. Fixes to challenge 2. Decrease the similarity threshold. Make the similarity requirement stricter to filter out less relevant results. Decrease the number of results to return. Return fewer results, focusing on the most similar ones. Langchain Fireworks Chat Models Summarization. These chat models integrate with langchain and Fireworks, leveraging the power of both frameworks to create powerful and versatile conversational AI systems. Langchain provides the infrastructure for connecting various components like language models, data sources, and tools, while Fireworks offers a platform for managing and deploying these models. This combination allows for the creation of chat models that can access and reason over vast amounts of information, generating insightful and informative responses. Inputs: user prompt, which is the text input provided by the user, and system context, which refers to any relevant information provided to the model beforehand. These inputs are crucial for the model to understand the user's intent and provide appropriate responses. For example, a user might ask, "What is the capital of France?" in their prompt, and the system context could provide background information about France, data or knowledge base for retrieval or reasoning, which is the source of information the model uses to answer user queries. This could include documents, databases, APIs, or any other relevant data source. A chat model might use a database of world capitals to answer the user's question about the capital of France. Outputs: chat responses generated by the model, which are the outputs the model provides to the user based on their prompts and the information retrieved from data sources. These responses should be relevant, informative, and coherent. The model could answer Paris to the user's question about the capital of France. Log of model interactions for debugging and analysis, which records the model's internal operations, including the prompt, the retrieved data, and the reasoning steps taken to generate the response. This log can be useful for identifying errors, improving model performance, and understanding how the model works. The log could record that the model retrieved the information Paris is the capital of France from its database before generating the answer Paris. Steps: initialize the model and load necessary components, which involves setting up the model's environment, loading any pre-trained weights or parameters, and configuring the necessary components like data sources and tools. This step prepares the model for interacting with the user and processing their inputs. For example, the model might load the pre-trained language model, connect to the database of world capitals, and configure the necessary reasoning tools. Pass the user prompt and extract relevant information, which involves analyzing the user's input to understand their intent and identify key concepts. The model might use natural language processing techniques to identify the keywords capital in France from the prompt "What is the capital of France?" Retrieve relevant information from data sources, which involves accessing and extracting information from the data sources specified in the system context. The model might query the database of world capitals using the keywords France and capital to retrieve the relevant information Paris is the capital of France, reason over the retrieved information and generate responses, which involves processing the retrieved information and formulating a coherent and informative response to the user's prompt. The model might use its reasoning capabilities to identify that Paris is the answer to the user's question based on the retrieved information. Prerequisites: langchain library installed and configured, which involves installing and setting up the langchain library, ensuring that it is properly integrated with the model's environment, and configuring any necessary dependencies. Langchain provides the necessary infrastructure for connecting the various components of the chat model, enabling seamless communication and data flow. This could involve using a package manager like pip to install the langchain library and configure its settings according to the specific requirements of the chat model. Fireworks SDK and Application Programming Interface Access, which involves installing and configuring the Fireworks SDK, ensuring the model has the necessary permissions to interact with the Fireworks API, and setting up the necessary authentication credentials. Fireworks provides the platform for deploying, managing, and monitoring the chat model, allowing for efficient and scalable deployment and integration with other systems. This involves downloading the Fireworks SDK, obtaining an API key from Fireworks, and configuring the model to use these credentials for communication with the Fireworks platform. Fine-tune parameters, model weights and parameters, which are the internal settings of the model that determine its behavior and performance. These parameters can be fine-tuned to improve the model's accuracy, efficiency, and responsiveness. For example, adjusting the model's weights and parameters could improve its ability to generate more relevant and coherent responses. Retrieval and reasoning strategies, which are the methods the model uses to access and process information from data sources. These strategies can be fine-tuned to optimize the model's performance based on the specific requirements of the task and the available data sources. For example, different retrieval algorithms can be used to improve the efficiency and accuracy of information retrieval, while various reasoning techniques can be employed to enhance the model's ability to draw inferences and generate insightful conclusions. Response generation settings, which determine how the model generates its responses. These settings can be fine-tuned to control the style, length, and complexity of the responses, ensuring they are appropriate for the target audience and the specific context of the conversation. For example, the model's settings could be adjusted to generate more concise and informative responses for a factual query, while generating more creative and engaging responses for a conversational task. Challenges and fixes. Model hallucinations or incorrect responses, which refer to the model generating inaccurate or misleading information due to biases or limitations in its training data or reasoning capabilities. Addressing this challenge involves improving the quality of the training data, refining the model's reasoning logic, and providing feedback to correct any errors or biases. This could involve using more reliable and diverse data sources, implementing more robust reasoning techniques, and incorporating user feedback to identify and correct inaccuracies. Limited access to data or knowledge sources, which can hinder the model's ability to retrieve and process information necessary to provide comprehensive and informative responses. This challenge can be addressed by expanding the model's data sources, integrating with external application programming interfaces, and leveraging knowledge graphs to access a wider range of information. This could involve adding more relevant databases, APIs, and knowledge graphs to the model's data sources, ensuring it has access to a broader and more comprehensive knowledge base. Performance issues or slow response times, which can negatively impact the user experience and hinder the model's efficiency. This challenge can be addressed by optimizing the model's architecture, leveraging caching mechanisms to store frequently accessed data, and parallelizing operations to distribute the processing workload across multiple cores or servers. This could involve using a more efficient language model architecture, implementing caching mechanisms to store frequently accessed data, and leveraging cloud computing resources to distribute the processing workload across multiple servers. Langchain Fireworks LLMs Fireworks Summary. Large language models LLMs are powerful deep learning models that can generate code in various programming languages. LLMs can be trained on vast amounts of code data, allowing them to learn complex syntax and patterns. They can then generate code based on natural language prompts, making it easier for developers to create programs without needing extensive coding knowledge. Inputs. Code prompt. This is a natural language description of the code that needs to be generated. For example, you could prompt the LLM to generate a Python function that calculates the factorial of a number. Programming language. Specify the programming language for the generated code. Common choices include Python, JavaScript, C, and Java. Outputs. Generated code. The LLM generates the code based on the provided prompt and programming language. The generated code should be syntactically correct and functional, ready to be implemented in the desired application. Steps. Receive code prompt and programming language. The LLM receives the input from the user, which consists of the code prompt describing the task and the desired programming language. Generate code using the LLM. The LLM processes the input and uses its trained knowledge to generate the corresponding code. It considers the syntax and semantics of the chosen programming language and ensures the generated code aligns with the provided prompt. Prerequisites. LLM access. The user needs access to an LLM, either through a cloud service like OpenAI or by running their own LLM locally. OpenAI API key. This is a key provided by OpenAI to access their LLM services. It allows users to interact with the LLM and generate code via an application programming interface. API call. Code prompt. A clear and concise code prompt is essential for successful code generation. It should describe the desired functionality of the code in natural language. For example, write a function to calculate the area of a rectangle or create a web page displaying a list of products. Fine-tune parameters. Temperature. A parameter that controls the randomness of the LLM's output. Higher temperatures lead to more creative and diverse code generation, but it can also introduce errors. Lower temperatures result in more predictable and deterministic code, but it might lack creativity. Top P. This parameter is used for sampling the LLM's output tokens. It sets a threshold for the probability distribution of the tokens. Only tokens with probabilities above the threshold are considered for output. Higher top P values lead to more diverse and potentially unpredictable code generation, while lower values produce more deterministic and predictable code. Challenges and fixes. Code generation errors. The LLM might generate code containing errors due to limitations in its training data or understanding of specific coding patterns. To address this, users can try using a different LLM, modifying the prompt to be more specific, or manually reviewing and correcting the generated code. Code output issues. The generated code might not perfectly align with the user's expectations or might require further modifications. Users can review the generated code, adjust the fine-tuning parameters like temperature and top P, or provide a more specific and detailed prompt to improve the code output.